Everyone, today we are not solving any LeetCode problem. Today we have graphs and BFS, and we are going to go in depth about these two topics. We are going to understand what exactly is a graph. Is it just a node, edges and all that? Or is it something even more deeper? And then we are going to understand what is a BFS and how we can apply BFS to crazy situation like a simple array, which does not even feel like a graph at first look. So before we go ahead, I am assuming that you have some basic knowledge of graph. You at least know that there are nodes and those nodes are connected to other nodes. We can have multiple edges between multiple nodes. And I am also assuming that you at least know the concept of adjacency list and adjacency matrix. If you don't understand that properly, that is fine. But you must have some basic understanding of these two things and graph. Because in this video, we are going to go in depth in these graphs, and we are going to understand what a graph really is. We are going to see how we can turn something crazy like a simple array into a graph. We don't even need something like the adjacency list to actually, kind of create a graph. We are going to go in depth of these concepts. Suppose that we have this adjacency list. This is 0 index, this is 1 index, this is 2 index, and this is 3 index. And we are saying that at 0th index, in this list, we have stored another list. And this another list contains 1 and 3. So basically we have this array, and inside of this array, at each index or at each position, we are basically storing an entire list. So it is basically an array of list. So now if I want to create a graph using this adjacency list, how can I do this? One thing I know is that these indices are actually representing nodes, right? So I can say that I have a node 0. So I can simply create a node 0. That is great. And now at this 0th index, we have this list that is 1 and 3. So what this list is saying is that if I'm at node 0, I am allowed to go to node 1 and node 3. Okay, so let's just go to node 1 and node 3. So I will simply say 1 and then I will simply say 3. So with the help of this much information, I was able to create this graph, right? Now let's move on to this node, that is one node. So we have already created the one node here. Now the one node actually contains this list. This list is saying that from one node you can go to 0 node and you can go to the node 2. So here I have already created this edge from 1 to 0. So I am able to go to 1 to 0 already. Now I am also able to go to the node 2 from 1. So okay, let us go to the node 2 from 1. Great. Now let's move on to the next node, that is 2. So the 2 contains this list. We have 1 and 3. We are saying that from 2 we can reach 1 node and we can reach 3 node. So here we already have this connection from 2 to 1. So this condition is solved. But we also need to have a connection from 2 to 3. It means I can just create an edge here. That is great, right? So from this much information, I am able to create the graph till now. Now we have this last node, that is 3. So here in the array at 3 index, I am storing this particular list. And this list is saying that from 3 node, I can go to 0th node or I can go to 2 node. Okay. So I already have this 3 node here, correct? I can go to 0th node. So yes, I already have this edge. And I can also go to 2 node. So I already have this edge. So I don't really need to change anything in my graph. And with that, all of our adjacency list is done. And we are able to create this graph. Now I want you to notice something. We were able to create this graph because we were following a rule, correct? And the rule was saying that for every node, I am providing you a list of nodes that you can reach. So you must only go to these provided nodes from that node. And that is why we were able to create these edges from 0 to 1 and 0 to 3, correct? Because of that rule, we were able to figure out that 0 can only go to 1 and it can only go to 3. It cannot go to 2. Why? Because we don't have 2 in this list, right? So the rule restricts, or the rule says that you cannot go from 0 to 2. And similar case for all these other nodes also. So from this discussion, we can get this insight that this edge, what is this edge? This edge is nothing more than a representation of the fact that the rule is actually allowing us to go from this node to this node. If the rule was not allowing us to go from 1 to 2, we will not actually have this edge. But since we have this edge, it means that we are allowed to go from 1 to 2 because of that rule. It means that the edges of any graph is just a representation of some kind of rule. Now what that rule is, that will be actually given in the question itself. But that rule can change, can be twisted, can be done anything with that rule. But the fact is that These edges, they always represents whether you can go from one node to another node only based on the rule. So from this we can conclude a very important thing. We can conclude that a graph must have a rule. Graphs must have a rule because edges can only be created according to this given rule. Correct? So rule is really important. But there is one more thing which is important. These edges do not mean a thing if we do not have these nodes, right? So what is a node? Well, a node is basically a situation or a place or a configuration or a state. In the current example, we can say it's a place. Why? Because 0 here represents an index. It's a position. So we can say it's a place, right? So you are at the 0th place, then you are at the first place, that you are at the second place, then you are at the third place. And the rule, this rule is actually telling you that you can go from 0 to first and third position only. So if you're standing on this place, you are only allowed to go to third place or the first place. That's what the rule is saying. So a node can be place, state, configuration or situation. State does not mean the MP or Uttar Pradesh or something like that. State simply means the conditions of a particular thing at the present time. So for example, if you are a person standing on the 0th position, your state is that you are at a 0 position. Now you go to this position based on the rule, right? So your state is now is that you are at first position. So your state changed from 0 to 1, right? So that's why I'm representing this node as a state also. Now this node can be a configuration because suppose you have a Rubik's cube. In the Rubik's cube you have many colors, you have many configuration, right? So you can go from one configuration to another configuration by rotating some of its sides. So it means each configuration of the Rubik's cube can be considered as a node, and when you rotate one of the sides, you are going to another configuration of the Rubik's cube, right? The earlier configuration was C1, then you rotate a side and then you reach to new configuration C2 of the Rubik's cube. So each configuration can be considered as a node, and rotation itself is a rule, so that rotation will lead you to another state. So that's why I'm saying configuration can also be a node. In the same way, any situation can also be a node. If you go from one situation to another situation, that is a node. That particular situation itself is a node. So we can say that a graph is anything that contains a node, that is a place, state, configuration of some kind or a situation, and we have a rule which actually gives us a way to go from one node to another node. So it means we are not restricted to these kind of graphs where we have these kind of nodes, right? We don't need these kind of graphs where we have a class and we have to create nodes and we have to just go through them like that. We can have a simple array as a graph also. So now let us try to understand how a simple array can also be a graph. Suppose you have an array of integers, okay, a simple array, and from any index in that you can only go to 2i plus 1 index or 2i plus 2 index. Great. So we have this array of integers and we have this rule that actually only allows us to go to 2i plus 1 or 2i plus 2 indices. So let's try to create an array. I will have 1, 3, 2, 9, 8 and like just say 10. Okay. And the indices for these will be 0, 1, 2, 3, 4 and 5. Great. So now we can consider these as places, right? So 1 is at 0th place, 3 is at 7th place, 2 is at 2nd place, then 9 is at 3rd place, then 8 is at 4th place, and 10th is at actually at 5th place, right? So these are like places. And since these are like places, we can consider them as nodes. So the 0th node contains a value of 1. Do you understand this thing? So let's try to draw this thing also. So I will first of all try to draw the 0th node. So I will have a node and in that the value will be 1. Why? Because the 0th node contains the value 1. Then from this 0th node, this index, I can go to 2i plus 1 or 2i plus 2. So here I is what? I is 0, right? The index is 0. So 2i plus 1 is what? 2 into 0 plus 1, 1. And then 2 into 0 plus 2 is simply 2. So it means we have a rule that is saying that we can go from this place to this place only. So I will have an edge that is going to this particular node, that is a node at one position, and this node contains a value of 3. So I will write it like this. Similarly, I will have an edge from one to another node that will contain a value of 2. So we have gone through these two nodes, right? Now I will shift and we can say I is now at first position. So now where can we go from first position? we can go to 2i plus 1 and 2i plus 2 again. So 2 multiplied by 1 plus 1 is 3. So from first position, I can go to third position, right? So I will simply say, okay, from this node, I can go to a node whose value, the value here is 9. So I created the third position node here with the value 9. Similarly, we can go to another node which is 2i plus 2. So 2 multiplied by 1 plus 2 is fourth. So we can reach this fourth node also, right? And the value of the fourth node is 8. So it means from this node I can reach another node whose value is 8. Great, right? And now we have reached all the nodes that we could reach from this particular node. Now we can shift the I to this position and we have I equal to 2. So what is now 2i plus 1? So 2i plus 1 means 2 multiplied by 2 plus 1. It means 4 plus 1, that is 5. It means you can reach the fifth index from the second index. So I will create another edge from this node to a node whose value is 10, because the value of fifth node is actually 10, right? Similarly, we will have 2i plus 2. So 2 multiplied by 2 is 4. 4 plus 2 is 6. Now we don't have a 6 here. So it means we only have one edge from 2 to 10 here. So now we can also shift I again here on this particular position. And now we have I is equals to 3. 2 multiplied by 3 is 6. 6 plus 1 7. But we don't actually have 7. It means this node does not exist. Then we can go to 2i plus 2, which is 2 multiplied by 3 plus 2. 6 plus 2 8. So we don't have 8th node also, right? In the similar way, if you increment I to 4th position or 5th position, we will not have any more nodes that we can connect. So it means we were able to create this particular graph with the help of the rule that was provided to us and the nodes that were provided to us with the help of this integer array. So here also a graph is nothing more than a node, which is basically a place or position in this case. And then we have this rule that allows us to go from one node or one place to another position or place. So are you able to get an idea how anything can actually be considered as a graph as long as there is a node and there is a rule? Because we were able to create this entire graph with a simple array. Let us take another example. Here we are saying that we have an array of integers and the ith integer tells the maximum possible jump we can make from that index. Okay, so we will basically have an array like 1, 3, 7, 9, 10, right? Something like this. And we are saying that this number 1 is telling us how big of a jump we can take from this index to the next index. Since it is 1, so we can only take a jump of length 1, which means we will only land on 3. But here we see that we have a 3 index, right? So we can take a jump from 3 to 7. We can take a jump from 3 to 9. Or we can take a jump from 3 to 10. Because the maximum length of the jump can be 3. Similarly, from 7 we can jump to 9. We can also jump to 10. But we cannot jump anymore because we are getting out of the array. So it means we can only access this and this using 7. Similarly, from 9 you can only go to 10. So let us try to put the indices also 0, 1, 2, 3, 4. And here we don't actually have much use of the indices because we are actually dealing with these elements themselves. So if I try to create a graph, I will have a node with 1 and the number 1 means that the maximum jump we can take is from this position to next position. So it means that 1 will have an edge from itself to another node which is 3. Now let us look at this 3. So the 3 allows us the maximum jump length of 3. So I can go to 7, 9 and 10, which means I will have 3 edges from 3. So I will have an edge from 3 to 7 because I can reach 7 from 3. Then I will have a 3 to 9 because I can also reach 9 from 3. And then I can have an edge from 3 to 10 because I can also reach from 3 to 10. Then we will have this 7. So where can we go from 7? 7 allows us to have a maximum length of 7 indices. It means I can go from 7 to 9 and I can go from 7 to 10. It means I will have 2 edges from 7. First of all, I will have an edge from 7 to 9, which is this one. And then I will have another edge from 7 to 10, which is this one. I hope you are able to see the graph taking shape. Now let us go to this. So 9 have a maximum jump length of 9 places, which means we can go to 10th from 9. Of course, we can no longer go to any other place because everything else is out of bounds. These things do not exist, right? So we can only go to 10th. So it means we will have an edge from 9 to 10. So I will simply create it like this. Now understand one thing. I can only go from 1 to 3, right? In this direction. It means I have a directed edge. We are not allowed to go back. We are only allowed to jump forward, right? So I have a directed edge from 1 to 3. I can go from 1 to 3, but I cannot go back from 3 to 1. Similarly, we can go from 3 to 7, but I cannot go back from 7 to 3 because we can only jump forward. In the same way, I can go from 3 to 9, then 3 to 10. In the same way, I will be going from 7 to 9 and 9 to 10. This is basically an example of creating a directed graph using simple array and a rule. So the node here can be considered as a state. You are going from one state to another, and the rule here is jump length. So jump length is actually the rule that allows us to go from one state to another. And note that even though this rule is allowing us from going from 1 to 3, it is also restricting us to go from 3 to 1. We are not supposed to go to 3 to 1. In this earlier example also, we are only supposed to go forward. It means these are also directed edges. They are not two-way edges. And from the graph, you can also notice that it is a simple tree. So a tree is actually represented by this condition 2i plus 1 and 2i plus 2. So a tree is actually represented inside of an array with the help of these conditions, the 2i plus 1 and 2i plus 2 conditions. Now here is another very important example, that is two-dimensional grid. So we are saying that we have a 2D grid with the dimensions m multiplied by n, and we can only go up, left, right and down from any cell in the grid. Now suppose that we have this particular grid and we want to start from this particular cell. So how are we going to represent this cell? Well, we can use the row number and column number to represent it. So it is at row 1 and column 1, right? Now I can only go up, left, right and down. So it means let's just try to create a node here. 1, 1. This represents this particular cell. Now I can go up, right? So if I want to go up, I will simply subtract 1 from the row number to go up, right? So it means that I will have an edge from 1, 1 to 0, 1 also. Why? Because 0, 1 represents this particular cell. Great, right? Now if I want to go to the right direction, what is the coordinate? Well, in order to go to the right, you need to add 1 to the column number, right? So I will simply add 1 to the column number. So I will have the row number same and the column number will simply become 2. So that's how we will be able to reach this particular cell. And so if I want to go to this cell, I will have to subtract 1 from column number. So it will become 1, 0. So I will have another edge from 1, 1 to 1, 0. Now if I want to go down, how will I do that? If you want to go down, you will have to add 1 to the row number. It means I will have another edge from 1, 1 to 2, 1. So the row number is 2 and the column number is 1, which is this one. In a similar way, we can go to 0, 0 from here. So I will have an edge from 0, 1 to 0, 0, correct? And I can go to 0, 2. So I will have another edge from here to 0, 2. Now here's one thing. I have 0, 0, right? And from 0, 0, I can go to this 1, 0 also. Why? Because 1, 0 in the downward direction. So I will have an edge from 0, 0 to 1, 1. And in the same way, we can keep on creating this graph. So in the similar way, I tried to create the entire graph. So as you can see here, that we were able to convert this two-dimensional matrix into a graph because we had two things. We had nodes, and nodes in this case represent these particular states, or you can say positions, or you can say place. So these are represented by nodes. And then we have a rule. The rule is saying that we can only go up, left, right and down from any cell. That is why we have this particular graph. If we also allow the diagonals, so it means I can go to the diagonal directions also, this graph will become very big and very complex. But even then, we will be able to represent this grid with the help of a graph. So I hope that you are actually getting a sense that anything can be a graph as long as you have nodes and you have rules that govern how you can go from one node to another node. So now let us talk about breadth first search, or BFS. BFS is a way for us to go through each and every node in a graph. Suppose I have a graph like this. Now it may look like a tree because trees are also nothing more than special versions of graphs. But here you can start from any node. In trees, you will actually have a node like this, head node, and you will start from there. But in graph, you can start from this node, you can start from this node, you can start from this node also. So that's why we are calling it a graph. So you can use BFS to start from any node and go through each and every node in this particular graph. So how does BFS work, right? Well, BFS requires some initial configuration. First of all, we will need a queue. So we will have a queue like this in which we will store nodes. Queue is a data structure that follows first in first out principle. We have a FIFO principle. So whatever you place inside of it first, that will be the element that will get out of it the first as we pop it. So whatever goes inside of this queue first will also come back first. So let us number these nodes as 1, 2, 3, 4, 5, 6 and 7. So I'm starting from this node. I will take this node and I will put it here. This is the initial configuration what we are doing. Okay, we will have a queue. We will first take the starting node, we will put it into the queue, and then we are going to start the BFS. Now in the BFS, what you do is you take out the node from the queue. Now you can do whatever you want to do with the node. You can actually just console log it, you can perform some operations or whatever you want to do. After you have done whatever you wanted to do with the node, you will use the rule that is given in the question to figure out what are the neighbors or what are the other nodes connected to this first node, and then you will find those nodes and you will place them inside of this queue. So here I can see that 1 is connected to the node 2 and node 3. Now I have already popped 1, so queue does not have this node 1, but after doing these operations I will be putting 2 and 3 inside of this queue. So 2 will come here and then 3 will come here. Now I will again pop a node from the queue. This time the 2 will be popped because we entered the 2 first. So 2 will be popped. Then we will also again do operations, and then we will find the neighbors based on the rules provided, and then we will place them inside of the queue. So 2 has the neighbor 4 and 5. So I pop the 2, I perform the operations, and then I will place 4 and 5 inside of this queue. Now 2 has been done, right? It's already popped out, so it will no longer be in the queue. Now I pop again. This time 3 will be popped because it was placed before 4 and 5. So 3 popped, we perform some operations on this 3, then we again use the rules provided in the question to find the neighbors, and then we place those neighbors, that is 6 and 7 inside of this queue. So 6 will be here and then we will have 7 here, and now the 3 is popped, so 3 no longer exists in the queue. Now we have 4. So we will take out 4, we perform operations, and we try to find the neighbors for the 4 based on the rules given in the question. We see that we don't really have any neighbors anymore, so we do nothing. We just pop this one and we are just done with the 4. Now we will have 5. 5 will be popped, same. 5 don't have any neighbors. So whatever you want to do with this node, you do it, and that's it. 5 is done. Similarly, 6 will be done and then 7 will be done because they also don't have any neighboring nodes. So this is how the logical workflow of BFS works. Let me show you the code. So here is the BFS function that will go through each and every node inside of a graph. So we have the start node, and from this node we are going to start our BFS traversal. So first of all, we have this queue, and inside of this queue we are placing the start node. This is part of the initial configuration, and then we have something called visited set. Now the reason we use visited set is because one node can be connected to multiple nodes. So suppose that this fifth node was actually connected to the first node also. So when we were actually taking out fifth node, we were performing operations and we were trying to find the neighbors. We will find this first node as a neighbor, but are we going to add this one node again into the queue? Are we going to do that? No, we are not going to do that. Why? Because we have already traversed the one node. If we add it again, we will end up traversing the entire graph from 1 to the last node again. It will be an infinite loop. That's why we have something called visited set. So in the visited set, you will store the nodes that you have already visited. For example, I placed 1 in the queue, right? So when I place 1 in the queue, I will also place 1 in this set, so that I will know I have visited the one node, and if any other node have 1 as its children, I will not add this one node again into the queue. So that's why we have this visited set, and we are putting the start node inside of this set so that we will not end up actually adding this start node again in the queue. Now here the BFS actually starts working in this while loop. So what we are doing is we are checking if the queue is empty or not. So we are going to run the BFS while the queue is not empty. First of all, we will pop the node. Okay, so we have the current node. We will take the queue and pop the node. So initially we had 1 in the queue, right? So 1 will be popped and we no longer have 1 in the queue because popping the element simply removes it from the queue. We pop the 1, we store in this particular variable current node, and then here we can do whatever we want. Currently we are just printing the current node, but we can do whatever we want with the node. Now after this step is done, we are checking for all of its neighbors. So here the graph is basically the adjacency list. From this adjacency list, we are taking out all the neighbor node for this particular node, and we are checking if that neighbor is already visited. If it is not visited, we will add it into the visited set, and then we will add it into the queue also, so that next time we will be popping this particular neighbor. This is the step where we actually add 2 and 3. Now once this is done, we will again go back to this while queue. We will check if queue have some element or not. Well, yes, it does have these 2 and 3. So we will again go inside of it. We will pop the node. This time 2 will be popped. So 2 is no longer in the queue, we have popped it, and now we are printing the 2 and then taking all the children of 2 and putting it inside of this queue again. And in the same way we can go through entire graph. Now one thing to notice is that in the BFS, part from here to here will be basically the same. Okay, it's not really going to change all that much. But this part, the place where you are actually taking the children and placing it inside of the queue, that can change. The main logic will actually not change. You will place the neighbors inside of this queue, but how you are going to do that can change. Because currently we have this graph adjacency list, and that's why we are doing this particular thing. But adjacency lists have a rule, right? Because of which we are able to find the nodes connected to a particular node. What if the rule changes? What if we don't have the adjacency list? What if we are given an array and we have a rule that from any index you can go to 2i plus 1 and 2i plus 2? The same example that we saw earlier. What will happen in this situation? Now let us try to see how we can actually use BFS inside of this array, which represents this graph based on these rules. So we will again do the same thing. We will have a queue, and inside of it we will place the starting node. Suppose we start with 1. Okay, so we place 1 here. The queue contains 1, and we will also have visited. So visited will contain the 1 at this point, and then we will have this while loop where we are checking whether queue is empty or not. So if queue is not empty, we will go inside and we will take the current node. So we have popped the queue, right? So it means current node right now is 1. We have the current node, and this 1 is actually no longer present in the queue. We have popped it, okay? And here I can do whatever I want with the node. I will simply print it here for simplicity's sake. So I have printed the node, and now it is time to actually take the children of this node and place them inside of the queue. So how will I do this in this case? Because I don't have an adjacency list here. I simply have these conditions, right? So in these kind of situation, you will actually have to calculate the neighbor nodes yourself. Why? Because you don't have a list of neighbor nodes. You just have a condition that will tell you which are the neighbor nodes. So you will use these conditions to calculate it. Okay. So I will use this condition to calculate the neighbor 1. Now neighbor 1 will be equal to 2 into I plus 1. Correct? Neighbor 2 is equal to 2 multiplied by I plus 2. Right? Now one thing is that we don't have I right now. Correct? What this means is that in the node, storing 1 is not enough. We need to store its index also. So a node will look like this. We will have index 0 and we will have the value that is present at the index. So a node will be like this. So when we are popping it, the current node will actually have two things. Okay, it will have 0 and it will have 1, right? So we can take this 0 into a variable called I. So I will be equal to and then 0. You know, I can store this current node as 0, 1 inside of a node, right? I can store it as a list also. So that's why I'm using the index 0 to represent that I want this particular part of this stored list. Now I have I, and then I will simply calculate. So n1 currently is going to be 2 multiplied by 0 plus 1. So 2 multiplied by 0 plus 1 is what? Simply 1, right? So I will get this particular index 1 and I will store the value, and I will actually have to store these two things inside of the queue. Similarly for n2, we will have 2 multiplied by I, which means 2 multiplied by 0 plus 2, which is basically the second index. So I will have this stored in the queue. How will I do this? I will simply say queue dot append. Then I can append a list inside of the queue. I will say I want to append n1, which is basically the index of the element that we want to append. And then I can say nums of n1. So what we are doing is that we are taking the index and the value present at that index in the given nums array, and we are storing this inside of the queue here. So the queue will contain 0, 1 also. Similarly, we can do the same for n2. Queue dot append n2 and then nums or the element at n2, and this will also be stored inside of this queue. So the queue will now contain one more element, that is 1, 2, and the queue is basically this big right now. And in the next iteration, we will end up popping 0, 1 in this current pop, and then we will just repeat the same entire process again to store the new neighbors. Now understand that here you will actually have to check if this particular n2 is actually present in the visited or not. If it is not present in the visited, then only you append. So it means the condition will be like this. So if n1 is not visited, then only you append it. So if n2 is not visited, then only we append the n2 element inside of the queue. So I hope now it is getting clear to you that if we don't have adjacency list in the question and we only have these conditions or these rules, then we are supposed to use these rules to calculate the neighbors and then store them in the queue. So now let us try to understand how we can actually implement BFS on jump game example. In the jump game example, we had this kind of array, and due to this array, we were able to create this kind of graph. In the jump game, what we are simply doing is that we will take this value and we will know how many jump we can do, the length of the jump. Since it is 1, it means we can only go to 3 because the length of the jump is 1. But if we are at 3, we know that the maximum jump length that we can have is 3. So we can go to 7, or we can go to 9, or we can go to 10. Why? Because we have maximum jump length of 3. That's why in the graph 3 have edges to 7, 9 and 10. So jump length is the rule for figuring out the neighbors here. So here I'm doing the same thing as we did in the earlier example. We have the queue here, we have the visited here, and we are starting the while loop. Now I am popping the node here. So it means 0, 1 has been popped. It is no longer in the queue. Now here I am printing this value 1 by accessing it from the node. And then I'm accessing this index 0 with the help of this I variable from the node, because I is going to be used to figure out the next neighbors. So we know that the maximum jump we can make is the value of the element itself, right? What we can do is we can actually start a for loop that will run from 0 to the jump length, and the jump length is simply node 1, right? Because in this index we are storing the jump length, the element, right? So we will simply have this for loop, and the 0 is going to be k equal to 0 because we are going to use k variable inside of the for loop. So what we will do in the for loop is we will calculate the neighbors of the current node. So I will have a variable neighbor is equals to the index I, which we calculated here, and then we will add k. In the starting the k will be 0, it will return us I, which means the k should not start at 0, it should start at 1, so that we will not get the I back. Now the index at the starting was 0 because this is the element that we actually popped out. 0 plus 1 is what? 1, right? So what we will do is we will simply say q.append an index and the value at this index. So this is how we are going to add this thing. And this is basically a list. So we are going to add this thing inside of this queue, which means we just ended up adding 1 and 3 inside of this queue. So we will have 1, 3 here. Now in the next iteration, the k will become 2. But this thing is basically 1, right? So we are only supposed to run the loop till the maximum limit of 1. So it means as soon as the k become 2, this loop will end and we will go back to this while loop. We will check if the queue is empty or not. Since it is not empty, we will again go here. We will pop the 1, 3 here. Now we have 1, 3 in the node. We will print the 3. The element 3 will be printed, and then we will have this I. The I in this case will be what? 1, right? So the I will be 1, and then again we are going to start the for loop from 1 to this 3. So in the for loop we will have I is equals to 1 and the k will be 1. So 1 plus 1, 2, right? So we will have this particular element 2, 7. We will store it inside of this queue. Then the next iteration will happen. In the next iteration the k will be what? K will be 2, right? So 1 plus 2 is equals to what? 3. So we will have 3, 9 inside of this queue. So in the next iteration, we will have k is equals to 3. 3 plus 1 is equals to 4, right? It means we will end up storing this particular index or this particular node inside of the queue. So we will have 4, 10. And now this loop has been run 3 times. So this for loop will end, and now after ending we will go back to this while loop. We will pop the 2, 7, we will calculate its neighbor, we will put them in the queue. The same process will repeat for all these nodes. So in this way we are using the given condition of jump length to calculate the neighbors of a given node. Now of course there are a few checks that I've skipped. So before appending something into the queue, you need to check if it is already existing in the visited or not. So you will have a if condition checking if n is already in visited or not. If it is not in the visited, then only you append it. That is a very small thing that you can figure out on your own. Now we will try to perform the BFS on 2D grid and see how we can calculate its neighbors. So first of all, we are going to start from this particular cell, the middle cell. That's why I have placed the 1, 1 inside of this queue. Now we have the visited set, so visited will also have 1, 1 in the earlier stage, and now we are starting the while loop. So while the queue is not empty, we are going to pop the node. So node will be popped, and then we are getting row and column. So this node has been popped, it is no longer in the queue. The row will be 1 and the column will also be 1 at this point. So it will be equal to 1 and 1. So row is 1, column is 1. Now we have to find out the neighbors of this particular node, particular state or this particular place. Then what we can do is we can use the given condition. In the original example that we discussed earlier, we could only move up, left, right and down. These were the only 4 directions in which we could move from a given cell. So it means at maximum we can have 4 edges from each node. So we will calculate the node at up direction. So I have row and column. If I want to go up, then I need to subtract 1 from the row. then I will say the up is row minus 1 comma original column, so column will not change. Similarly, right will be equal to, well, in case of right I need to go from 1 to 2, it means I will need to increase the column number, right? So I will simply have row as the same and the C, the column number will be increased by 1. Similarly, if I want to go to left, the column number will decrease. The row number will be same, the column number will become C minus 1. Why? Because going from 1 to 0, I need to decrease 1. In the same way, I can also calculate the down direction also. So for the down, I will simply increase the row by 1 and I will keep the column as same. So these are the 4 nodes that I will have available to me to place in the queue. Now, of course, I will check whether these nodes are actually existing in the visited or not. But if they do not exist in the visited, we will simply take them and place them inside of this queue. Simple, right? We are using the given condition inside of the question to actually calculate the possible neighbors. So all these nodes will be placed inside of the queue, and then you can simply use q.append up, q.append right, q.append left, q.append down. That function will change from language to language. I'm using Python, so I can use append function. But you see the function that is present in your language for you. Now here is one topic that you need to understand about BFS. In BFS, we are going from level to level. First, we will take all the nodes on this level, the level 0. Then we will take all the nodes on this level, the level 1. And then we will take all the nodes on this level, level 2. But right now we don't have any way to figure out whether the node that we popped from the queue is actually at level 1 or at level 2. So how can we figure that out, right? So here we have our normal BFS. We are starting from this node. So we will store 1 here already. Then we will have 1 here already before starting the while loop. And if you notice, the length of the queue currently is what? 1, right? Currently, there is only one element inside of the queue, so the length is 1. And we will be always sure about it because we are going to start with a single node always. So it means the 0th level will always have one node. So to track the level that we are currently on, we can have a variable like level and we will initialize it with -1. Okay. Now as soon as we get inside of the queue, we will simply increment the level by 1. So level will be level plus equals 1. So level at this place right now is 0. Because earlier it was -1, right now it is 0. And now here is the main thing. Right now we are taking just one element from the current level and we are doing it, right? Which is fine because there is only one element right now. So we take one and we just take all the children of the one and we append them here. Okay, so 2 and 3. But if I try to run this loop now, we will have 2 at this point, correct? So this loop will only run for 2 and then we will again go back to while loop. And once we go back to the while loop, we will take the 3 out. And at this point, we will again increment the level by 1. So level actually will become at this point 2. But we are still traversing the elements of level 1 only. So what do we need to do? We need to actually take all the elements present in the queue and we need to run the for loop together for all the elements. Then only we will come back to while loop. So to do that, we will have another variable current length of queue. Okay, so in this current length of queue, we will calculate the length of queue that we currently have. So it will be equal to len queue. And then we will use this variable to place everything here into a for loop. So we will run from 0 to current length of queue, so that all this logic will run for every single element that is currently present in the queue. And once we have covered all the elements, then only we will go back to the while loop and then only we will actually increment the level. So level will not be incremented here. It will be incremented before this for loop here in the while loop. So level will be incremented here after the while loop and before this for loop. So level will be level plus 1. And now the level will be properly updated each time. So first we will get this node. We will run this for loop for this particular length, that is 1 length. It will run, we will increment the level by 1. So it will become 0. And then we will have 2 and 3 inside of the queue. We will get back into the while loop. We will be inside of the for loop and we will run this for loop for both of these elements. So it means we are going through all the elements of the current level before going back to the while loop. And that is how you are going to track the level that you are currently on in a BFS. I know it may be a little messy, but you will have to practice on your own to understand these kind of things. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.